Hello everyone, and welcome to this new review session. In this chapter, we're going to talk about waves and frequency. So let's just warm ourselves up with reviewing the same notions that we have learned before. So period is the time required for one full cycle. And the unit should be in seconds. And frequency is the number of cycles in a second. And the formula to connect these two notions is T equal to 1 over F. And one thing you need to be aware of is that any object that has oscillatory motion following Hooke's law, where the restoring force is proportional to the displacement, is said to undergo simple harmonic motion. One important concept we have to be aware of is that acceleration is proportional to the negative displacement. So how do we get that? So we know about Hooke's law, in which the restorative force of the spring is equal to negative kx. And the negative here, we can interpret it as it always points towards the equilibrium. And from that, we can plug in Newton's second law, of which it states F is equal to ma. And when we associate these two factors together, we get a formula of ma is equal to negative kx. Proceeding from there, we manipulate for a. That's where we get a is always proportional to the negative displacement. One thing to notice is that this statement only works when mass is constant. One more thing to talk about before we move on is amplitude. Amplitude is the magnitude of an oscillation measured from its equilibrium position. So note that the period is independent of the amplitude. So here T is the period in seconds, M is our mass in kilograms, and K is the spring constant, which is Newton per meter. And for pendulum, note that the period is independent of the mass. And here the same thing. T is period in seconds. L is the length to the center of the bob, or the mass, we can say. And the unit should be in meters. And G is the acceleration due to gravity, of which the unit should be in meter per second squared. One more thing I would like to mention about this formula for pendulum is that this equation works only for small angles and small displacements. Having said all that, let's work on some examples. A centrifuge spins with a frequency of 50 Hz. Determine the period of the centrifuge's spin and the number of rotations in 90 seconds. Okay, so we know that period is equal to the inverse of frequency, and that we are given the frequency is 50 Hz, so we plug it into our formula. And we get .02 seconds. We keep this 0 because we have two significant digits. Moving on to question B. It asks for the number of rotations in 90 seconds. we're given 50 hertz and then times 90 seconds. Another way we can view hertz, specifically in this question, is cycles per second. So that when we manipulate with the units, it's obvious that we get 50 times 90 cycles. That gives us 4,500 cycles. And we're done with the question. Okay, let's look at another example. A 1.2 kilogram object vibrates with a frequency of 0.75 hertz at the end of a horizontal spring along a frictionless surface. Determine the period of the oscillating mass and the spring constant. Okay, so let's list out what we're given first. We know that mass is equal to 1.2 kilograms, and the frequency is equal to 0.75 hertz. What we need to calculate is the period, T, and our spring constant, K. So again, utilizing the formula, period is frequency inversed. We get 1 over 0.75 hertz is equal to 1.3 repeated seconds. This gives our period. For question B, since we now obtain the value of period and mass, we can use the formula for spring, which is T is equal to 2 pi times square root of m over k. So we can manipulate the values around until we can isolate what we need to get. After manipulation, this is what we can use to plug in our values. After plugging in, we get K, the spring constant, is equal to 26.6479 newtons per meter. And if we take a look at the number of sigdics, which is 2, we then round it to 27 Newton per meter. And we box our answer. Okay, next, let's talk about waves. So some key concepts we need to know is that energy can be transferred from one location to another by one of two fundamentally different ways, using either particles or waves. So, properties of waves may include the following. First of all is source, which is anything that vibrates to create a disturbance and a wave. And then a medium. A medium is simply the substance a wave travels through. The frequency of a wave is equal to the frequency of the source. Do note that the speed of a wave depends on the nature of the medium it is traveling through. Another crucial element about waves is wavelength, which we also denote as lambda. So a wave's wavelength is the distance between successive crests or troughs. And as we also mentioned before, the amplitude is the magnitude of an oscillation measured from its equilibrium position. As the amplitude of the wave increases, so does its energy. And for sound waves, the amplitude represents the volume. And for light, amplitude represents its brightness. Reflection occurs when a wave collides with a straight barrier. The wave reflects off the barrier. And for reflection, we do need to know about the law of reflection, which states that the angle of incidence is equal to the angle of reflection. If we were to draw it, it will look something like this. Reflection occurs best when the reflecting object is at least as large as the wave's wavelength. At a junction or boundary between two mediums, a wave may reflect, absorb, or transmit. So, a really omnipresent example can be light hitting a window, of which it travels through air and then glass and then air again. It's a really familiar case, right? Reflection occurs when a part of the light bounces off the surface of the glass, and that's why you see glares on windows. And then transmission occurs when most light passes through, because you can see through the glass. And then absorption is a small fraction that has been absorbed as heat in a glass. So in this case, you just get all three at once. Two basic types of mechanical waves. I'm going to give you a second to try to recall these two waves. Okay, so the two types of waves that we have for mechanical waves are transverse waves and longitudinal waves. So transverse waves, aka sine waves, are waves where the particles of matter vibrate perpendicular to the direction of the wave's motion. And longitudinal waves, aka compression waves, are waves where the particles of matter vibrate parallel to the direction of the wave's motion. As we can see from the diagram shown below, the top is our crest, or peak if you prefer to call it so, and the bottom is our trough. Here from our top to the equilibrium is our amplitude. And on the diagram here, from the beginning to the end, is our wavelength, or of which we also call lambda. For longitudinal waves, okay, that's the best I can draw for longitudinal waves. So you get the notion of it. This part is obviously where it is more compressed, and this part is where it appears to be more stretched out. It's rarefaction. But the name doesn't matter that much. So on longitudinal waves, the part that is being bracketed is our lambda. Okay, so the universal wave equation and period frequency relationship is V is equal to lambda times frequency, and our old customer period is equal to 1 over frequency. Okay, having talked for all that, let's work on some examples. A tourist shouts across a canyon. The sound wave she creates travels at 340 meters per second across the canyon and reflects off the opposite rock wall. She hears the echo 1.01 seconds after she shouts. Calculate the width of the canyon. Okay, so here we are given the speed, which is 340 meters per second, and our time is this much. And we need to calculate for the width, which we can also consider as the distance. So utilizing our formula from kinematics, we know that speed is equal to distance over time. After we manipulate this formula, we get d is equal to vt. And we plug our given values in, 340 meters per second, don't forget your units, and 1.01 seconds. We obtain the value of 343.4 meters. And then because we know that the sound wave travels back, it hits, and then it comes forth. So we know that the time it takes here, 1.01 seconds, is the amount that it travels back and forth. So what we need to do is we divide it by 2. We divide the distance we just obtained by 2 to get our single trip distance. Okay, that sounds weird. Anyways, our value is 171.7 meters. Because here we have, let me see, we have 3 significant digits, right? So it should be 172 meters, and that's our answer. Okay, if you also get that track, good job. Okay, let's look at another example. Transverse waves traveling along a rope having a frequency of 12.0 hertz and a wavelength of 2.4 meters. Determine the speed of the waves. Okay, this one's pretty fundamental. I'm gonna pause and give you a second to work on it. Okay, so what we're given is 12.0 hertz of frequency and 2.4 meter of lambda, our wavelength, and we're asked to calculate its speed. So we just refer back to the universal equation, v is equal to lambda f, and plug in the values. What does that give us? 2.4 times 12.0 is 28.8 meter per second. Yep, that's correct. And let's check our sigtics. We have 3 sigtics, so yeah, it remains in the correct value. So we know that diffraction is the bending or spreading out of waves as they pass through an opening or by a corner. Okay, so what does it mean? Let's look at this diagram below. So here before the waves pass through the obstacles, they were straight. And then after they move through, they are diffracted. So remember that waves diffract, but particles do not. This is an important and defining characteristic of waves. And also, as the wavelength increases, the amount of diffraction increases. And for sizable diffraction effects to occur, the width of the opening, that's the width of the opening, must be the same size or less than the wavelength of the wave. Lower frequency waves diffract more than high frequency waves. Okay, and then interference. So interference occurs when waves meet and superimpose upon each other. Waves may add to each other to produce a larger wave or a smaller wave. So when it comes to interference, there are 2 types. One is constructive interference and destructive interference. So constructive interference occurs when 2 waves add to produce a resultant wave with larger amplitude than either of the original waves. And, well, intuitively, destructive waves occurs when 2 waves add to produce a resultant wave with smaller amplitude than either of the original waves. Okay, now we get the gist of it conceptually. Let's draw a diagram just to enhance the understanding. Here is our original waves. One is moving this way, one's moving that way. And when these two meet, it will look something like this. This is called constructive interference. There's a larger amplitude. You see, it was originally like that. Now it's like that. So the amplitude dramatically increases. Okay, now let's look at the diagram for destructive interference. Same thing. One is traveling like that. This time the other is traveling like this. That's their direction. And what will happen when they interfere? Think about it. Yes, they will cancel out. There is nothing left. Because the amplitude, they cancel out each other. In destructive interferences, it is not necessary for the resultant always to cancel out. It depends on the magnitude. And resonance is the vibration that occurs in an object when it experiences a periodic force with the same frequency as the natural frequency of the object. When sound waves form in a column, such as a wind instrument, the sound waves form points of constructive and destructive interference. This is a resonant effect. Now let's look at 2 scenarios. Scenario 1 is 2 that is closed at one end, and another is 2 that is open at both ends. And okay, this is our tube in a 2-dimensional form. Okay, so we have our node like that, extending all the way to our antinode. So here is our fundamental frequency. If this is our length, then we are going to express it as lambda over 4. Why is that? Because then it's going to look like we go up, and then here, and then here, and then here. This might not appear obvious, but it is being, our wavelength, our lambda is being divided up into 4 parts, and that's why we put our length here, our fundamental frequency, as lambda over 4. And then let's look at the tube open at both ends. happens? We start from our antinodes because they're open, you see? Open. Ooh, that's satisfying. We have our node here, and then here's our antinodes. So this is also our fundamental frequency. This time, what is our length? Our length is going to be lambda over 2. Why? Again, let's look at our full wavelength. If you start from here, then the full wavelength is going to look like this. And what is our pre-existing right now? It's this part, which is 1/2 of our wavelength. So that's why our fundamental frequency is lambda over 2. And then if we go on, this is our second harmonic. And here, what is our lambda? It's this part, right? Our wavelength. So we can see that it takes up the full length, which is our lambda. So that's why it's 2 over 2 lambda. And then here, we apply the same concept. This is our lambda, and what do we see here? We have half a lambda extending. Right, so it became our third harmonic. Or we can call 3 times FF our fundamental frequency, right? Here is 2 times FF. And how to express this? This is L is equal to 3 lambda over 2. Did you find a pattern here? It's 1, 2, 3. Simply depending on your wave pattern in the tubes. And moving back to our closed tubes. This is still our fundamental frequency. And then when we move on, we still start off from our node. And then here. This is our second harmonic. But what's the thing that you noticed here? Yes, this part is closed. It's a node, which means that there is no resonance. No resonance because it's a node and it cannot create any resonance, right? Okay, let's see what happens next. This is our third harmonic. 3 times FF. Does resonance occur here? Yes, because it's open-ended. Here is 3 over 4 lambda. You see, that's almost 1 lambda, but just this little part that we need to compensate for. Oh, we're still missing, so that's why it's 3 over 4 lambda. And then here's our fourth harmonic. Did you find out something? Yes, it's still a note here, which means that there is no resonance. Despite the fact that it is 1 full lambda. It still doesn't matter, I don't care. It's just you guys have a node, so that there is no way for resonance to occur. And what is the rule that pretends you guys found out? Yes. It's an easy way to remember. For the closed end tubes, whenever there exists the lambda with an odd number, it means that there is resonance. Whenever there is an even number, for example here 4 over 4 and here 2 over 4 lambda, there's no resonance because it's a node. Okay, now we get the gist of that. Let's move on to a new concept. Okay, our new notion is about standing waves. Waves can't stand, can they? Of course they can't. We're just talking about the metaphoric version. Standing waves. Right? We're not using personification at all. Okay, standing waves on string. Again, we have our fundamental frequency. This is 1/2 lambda, right? A full lambda will look something like this. Here is our fundamental frequency. 1/2 lambda. first harmonic. And then moving on, we have, this is our 2 over 2 lambda, which is a full wavelength, as we can perceive from here. Right? This is our second harmonic. This is really easy because you don't really need to memorize anything. Well, you do need to memorize the principles, but that's it. It's not like the annoying tubes where you have to distinguish whether it's open or closed-ended. This is our third harmonic, and etc. It just keeps on proceeding. So standing waves are produced when 2 identical waves traveling in opposite directions interfere, producing points of maximum amplitude and points of minimum amplitude, these are the minimum amplitudes. We also call them nodes. And here is our maximum amplitude, which are also our antinodes. These nodes and antinodes remain in the same location, causing the wave to adhere to standstill. Maybe one thing that you do need to know is that standing waves do not transmit energy. Traveling waves do. Okay, now let's work on an example question. The A note above middle C on the piano, called A440, whatever, is frequently used to tune instruments. An A440 Hz tuning fork is held over the open end of a closed tube, and the tube resonates. The temperature is 27 degrees, and the speed of sound is 347 meters per second. Determine the distance between the resonance points in the resonating tube. I'm just going to give you a second, and you guys can try to work on it. Okay, I assume you guys have tried on it, so let's go. We are given speed is equal to 347 meters per second. Frequency is 440 hertz. And what are we asking for? We are asking to get the distance, which we can also denote as length here, because it's in a tube, right? Again, we plug in the values into the formulas. But before that, let's manipulate for what we need. Here we need lambda. After plugging in the values, we get 140 hertz. We get 0.7886 meters. Because this is not our final answer, so we do not need to consider about the second exit. I mean, you can if you want, but it's just redundant process. Then, let's calculate for our length. So the problem here is that it did mention this is a closed-end tube. So length here is a problem, because we know that in a closed-end tube, resonates only occur starting from a quarter of lambda, and then accumulating half a lambda each time. This is where resonance occurs. And since we are asked to calculate the distance between the resonance points, we should calculate their difference. Our delta L is equal to 3 lambda over 4 minus lambda over 4. That gives us what? Lambda over 2. Yes, that is the distance between the resonant points. So right now what we need to do is plug it in. L is lambda over 2. L is equal to 0.7886 meters over 2. That gives us 0.3943 meters. Now let's take a look at the sigfigs. It is 3 sigfigs because even though the 27 degree exists, it is not the information that we used, so we do not take it into consideration. So here the least amount is 347, 3 sigfigs. And our answer will become 39.4 centimeters. And we're done. Okay, so one last thing that we're going to talk about in our review session is the Doppler effect. So the Doppler effect is the change in frequency or pitch as a wave source moves towards or away from an observer. If a sound source and detector are getting closer to an observer, the frequency will increase. That's intuitive, right? Which means that it is heard as a higher pitch. And if they are getting further apart, the frequency will decrease, which means that it's being heard as a lower pitch. The Doppler shift applies to all types of waves, both mechanical and electromagnetic. So, the formula for a Doppler effect. The frequency of a moving source may be found using F is equal to Fs bracket V over V plus or minus Vs. This is our formula. It's very standard prime because that's what we are obtaining, right? So here, f prime is the frequency detected by the observer. Fs is the frequency. Sorry, the frequency emitted by the source. V is the speed of the sound wave. And Vs is the speed of the source. Both in meter per second. And use negative if the source is moving. And use negative if the source is moving towards the observer. Just another little add-up. The proper formula should include the speed of the observer as well. In most cases, they are stationary. But we shouldn't take that into account just in case there exists a question that has a non-stationary observer. Okay, so let's work on one last example of this review session. An observer hears a frequency of 503 Hz as a police siren approaches her at a speed of 28 meters per second. Determining the frequency, the observer will detect if the police car were stationary, assuming the speed of sound is 335 meters per second. So we're given the speed of the source, which is equal to 28 meters per second. And our observer is stationary, which means that there's no speed. F prime is equal to F V plus over our frequency given, which is 1, and then our velocity of the sound waves is 335 meters per second as stated in the question. Okay, so now we plug the values in. It says that the observer hears a frequency of 503 Hz as the police siren approaches her. So this is it. This is the frequency when the car is in motion, which is our resultant frequency. And what we need to obtain is this frequency when the police car is stationary. We can put the values in first. Okay, so now the question becomes, what sign are we going to use? Is it positive? Is it negative? Well, we remember saying that use negative if the source is moving towards the observer. What is happening right here? It says approaches her, which means that it's moving towards the observer, right? So that's why we need to use negative. We'll put negative in. After a redundant process of calculation, we get 503 divided by 335 over 307. That gives us 461 Hz after rounding. Okay, we're done with the question. Congratulations for making it through another review session. Bye for now.